Welcome. Uh, I have made, I think, three videos in Dynamics. Hope you have liked it. It is still in the process. Let me remind you that if you like these videos, do share and subscribe. If you have any issues, please kindly make it a point to give any comments. I started off with Newton's laws of motion, gave explanation theoretical of first law, second law, third law, and we have looked at how one law could be derived from the other law. I mean, there are some of the things that we already did. Now, then I went on to look at the fundamental forces in nature. We found out the three forces: gravitational, nuclear, strong, and then electroweak forces, or electromagnetic forces, if I call any one of them by any one of those names. The electromagnetic forces we have to look at in the day-to-day scenario. Day-to-day we come across rope, chains, strings, etc. You have tension coming into play, friction, normal force, spring force. I think that the four forces that I'm going to deal with in great detail. While dealing with that, I keep on applying Newton's second law everywhere. I do make use of integrations wherever possible. I've already done that, and I started off with tension. And tension, I also made it a point that it's not always a pulling force unless you take only flexible strings or so. Otherwise, it could be pulling as well as pushing. You take a rigid rod. All right. Now, as far as heavy ropes are concerned, tension differs from point to point, and as far as light ropes are concerned, the tension remains the same everywhere. This is what we have already seen. But I gave an exception to this, that when the light rope passes over a heavy or rough pulley, the tensions differ on both sides of the pulley, right? And I think we've tried to do that. And then the last class, I looked at a few cases of tension and then pulley. The first pulley case was that of a fixed one. Two bodies are attached with certain masses, and this is what we generally call as a good machine. And I tried to write those equations from the dynamics, and then we knew that how we could not solve those set of equations unless you arrive at some other equations, some other relations, which we generally call them as kinematic relations or constraint relations. Any one of them you can call it, because the movement of one body is dependent on the other body. There is no dynamics involved there. So we use dynamics and derive the equation. Then we do constraints and get the equation. I did the simplest possible case the other day. But since this technique you don't come across in many books, what I would do is I repeat that what I have done in my last class, just for the benefit of all of you. When you take a fixed pulley, this rope, it has two segments, I told you. Now each segment has two edges, and whether both the edges move or one edge moves, you see. Now when I want to see, I fix one and look at the other one. Now I have taken, in this case, say it is accelerating down, for example. So when I fix it, now this lower body is somewhere here. Going down means what is happening to the segment? Increasing. So the segment increases due to this moment by S1. Then I fix this, and look, this is also fixed. If the pulley moves only, you will have to do. The pulley is fixed, therefore the second edge doesn't move. Now come to this. Supposing A2 is also given like this. So fix this. Now look at it is going down, therefore plus S2. Now fix this, and this is also fixed. the total algebraic sum of all those edges must be 0 because the total length is constant. So some of the changes must be 0. Some are positive, some are negative, likewise. So if you differentiate, you get velocity relation. If you further differentiate, you will get acceleration relation. Right? This which you could work out even by taking length of this body from any standard thing and write the length of each row, differentiate because the length remains constant. This is the essence of what I discussed in my previous lecture. Right? Now, we will look at various possible scenarios of these constraints. Okay. Now, I will do here, this is a table, there is one body attached, another body attached, this is one, this is two, say this is three. I am giving A1 is like this, A2 is like this. Now you always look at, if they give A1, A2, A3 or V1, V2, V3 or for that matter even S1, S2, S3, you take as they are, accordingly you have to give your relation. First of all, before the dynamics, I'll first look at the kinematics or the constraints. Now look, this is one segment, this is another segment. This is one edge, this is another edge. So what is happening here? This is anyway fixed. So what is happening? Decreasing, segment is decreasing. So what do? I can now directly put it in terms of even velocity, acceleration also. But for the time being, I am putting minus S1. This is fixed. Now, what is happening? This is going down. Now, down means the segment is increasing. So, we will call it as plus S3. So, this whole segment has given minus S1 plus S3. Now, look at this. The other segment, again minus. So, because it is decreasing, and from here to here it is increasing. So for this minus S2, for this plus S3, total must be equal to 0. What are you getting? 2S3 is equal to S1 plus S2. Alright? If you differentiate, further differentiate, these are the kinematics or the constraint relations. Oh, this is clear. How do you write the dynamics? Now here, look at the FPD of this. This is single row, so only tension and mass is M1, here mass is M2. So, let this go with the A1. So, how do you write? T is equal to M1, A1. There is no other force acting on this because it is moving horizontally. And similarly, if you draw FPD of this is also T. So, T is equal to A2. What about this? Let this be M3. Now there are two rows. One here, a single row. At 2 points it is pulled up. So you have T and T. Be careful about this. And here gravity acts. So how did you take it? A3 downwards. So how do you write? This force minus this is equal to M3 A3. Now A1, A2, A3, T, 4 variables, 4 equations, you should be in a position to solve it. That part of solving, I'm leaving it to you. It's a simple exercise. I think you can easily do it. Okay?